Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Delta, published in 1987 by Thalamus, coded by Stavros Fazolis, title screen by Lizard, apparently, the cover by David John Rowe and Mark William Erickson. Musician is, of course, Rob Hubbard. Now, this is one of my very early favourites from when I was much younger. What I want to do today, though, is that I want to have a quick little look at the game because it brings back so many memories. But then what I want to do is that I want to go into a little bit of detail on how the cheat codes would work in magazines, because I remember that a cheat listing was shown in Zap 64 way back in the day. And these cheat listings actually give a good insight in how to remove or to circumvent the protection in the game, because to be able to modify the game in such a way that you can have infinite lives or infinite time and so on and so forth, you need to be able to circumvent the protection all the way through the load until you get to the part of the game data that you want to modify the game code. So anyway, the tape version of Delta has this rather nice little loading effect at the very beginning. I seem to remember that the way that it did its auto run was a little bit difficult to understand at the beginning, but eventually I found out. But then, when I was greeted with this user playable Mixie load, I thought that this was a fantastic invention, right? Because it allows the user to play around with producing their own nice little musical ditties with varying effects, varying drums and bass, and of course the lead as well. I thought this was a fantastic way of spending the time during the tape load. Let's just listen to it for a little while longer, and then I'll just jump ahead until the title screen, because when the title screen came in, that was something really quite special. And then towards the end of the load we get this. Now this is actually where it's doing a lot of decompression. This game was compressed several times over. And then we get this marvellous title screen. Now when I first got this title screen I thought that it was using, as you would expect, a load of characters. But oh no, it's not using a load of characters. I mean, the stars in the background are, but we'll find out that actually it's using a whole lot of sprites. We'll look at that in more detail. So the game has this option of changing the number of players, but you can also add in-game music. This music goes on for quite some time during the gameplay. I remember you can play through to quite an advanced attack wave, if you like, or level through the game before the in-game music loops around. It's so atmospheric, it's fantastic. Many happy childhood memories playing through this game with the in-game music going. I mean, the sound effects are great too. Nice bassy sound effects, but this music is fantastic. And the way, when I was young and playing this game, the way that the game effortlessly, or seems to effortlessly, transition from one type of scrolling background to the other with nice little fading effects. It's like you're running through lots of different chapters. Anyway, enough of the game. So, to be able to understand how the listing works, we need to first look at what the listing is. Now in this issue of Zap64, issue number 26, on this page here, page 38 if I remember correctly, we have this listing. Now this listing has a for and X loop. It reads in values from the data statements, it pokes them into memory, and then it calls the machine code with that sys statement. Now to be able to understand, or to begin to understand how this is going to work, we need to understand how the auto run works with the tape version. So using my tape tool to inspect the tape version, we can see that it's going to do an auto run via the usual kind of vector that we would normally expect to see at the beginning there. So let's load some labels, especially kernel labels, just to make it easier to see what the code is doing in the machine code monitor. I've got all of my nice little web pages there from various different sources for the 0-page documentation and also the kernel disassembly. So you don't want to see me type in that listing. I mean, it won't take that long, but I'm just going to load the listing that I saved out previously. So this is the listing that was in the magazine. I just saved it to a disk image. 53186 is the start address in decimal. So we're going to put a breakpoint at 53186 so that we can see what the machine code looks like in the disassembly view. And this is what the code looks like. It sets up, where it claims rather the stop vector, and the stop vector is called very often when the screen is active and also during the load, because it needs to test the stop key. But what we do is that this cheat code claims the stop vector, and the stop vector continuously restores the default interrupt routine at 029F and 02A0, which is what the kernel tape loader uses to return back to. Now, the auto run code was loading over the top of this vector at 29F. So what it's doing, the cheat code first of all stops the auto run from working by restoring the default interrupt vector, as opposed to whatever else it was loading over the top. And then the code does a set LFS, a set nam, and then it does a JSR load at CFDA right there. So what this allows the cheat code to do is to then load the first part of the tape loader, but then not auto run, and then it can modify the tape loader that's just been loaded into memory with extra data. As you can see, that the stop vector was getting called. It was always being called by the kernel. So we insert the tape, and then we press play on tape to get the first code loaded in. We don't want to auto run the tape, we want to insert the tape because we're running the cheat code, right? We have a breakpoint just after the load finishes so that the auto run still is not going to run because it's been circumvented. The auto run has been switched off. So because the auto run has been switched off, we can see by looking at the screen behind the turned off screen, we can see that it's found delta and it's done the loading message. It would if it was allowed to print the ready message, but it's not gonna, because we're at the end of the load routine. We've just finished it. We can then disassemble the code that was loaded, and it's 29F here, 2A7. There we go. So we can see here that it's putting values of F5 and CF into 2ED. 2ED is somewhere in the loaded code for the Delta tape auto run that was just loaded, but it's not auto running. We are poking stuff into it, or rather the cheat code is poking stuff into it. Now it's poking CF F5. Basically, it's going to be pointing something inside the just loaded tape auto run code. You see it's loaded the auto run code into an unused area in memory. Actually unused, and the sprite 11 data area is also unused in the extended 0 page there. But yeah, basically it's saying to the auto run software, I want to, instead of you jumping to ed00 there, I want you to jump to my code, please. That's what it's going to set it up to do. And then it calls 351 in hex. It does a jump to 351 in hex, which then executes the auto run code, but with the cheat code modifications to call back into this area here. So it's going to call back into CFF5 instead of executing ed00. And then if you have a look there, you can probably see that it's going to be modifying what looks like a jump address and then jumping to ed00. So ed00 is probably the start of the Mixie load, I would expect. And we'll put a breakpoint at D002 because that's the address. But why is it using sprite 1x, which is basically the sprite 1x register in the VIC chip, in the video chip? Well, the video chip registers, the VIC chip registers, are read and write capable. So actually, if you put code in them and tell the computer, the CPU, to run the code from this memory address, it will actually run the code by reading it from the registers. Just because it's sprite registers doesn't mean that they cannot hold values. They do hold values, so the CPU can read that. It's not reading the RAM underneath the VIC chip, it's actually reading the data in the VIC chip itself, and that's going to be important. So we'll let this load continue, and we'll pick it up just as it hits the breakpoint that was meant to be at ed00, but now it's going to be calling the code in the cheat code. And here we go. There's the breakpoint that has hit inside the cheat code, and we can see that it's going to be probably modifying. Well, we can see that the calling routine came from the loader code, the tape loader code, all the way up at the extended 0 page at 2EA and so on and so forth. The code at 1CE is there, and we've got a jump to 2EB, which is where we get to this time. So instead of jumping to 2EB now, this is basically the next loader part. So basically the Mixie load, which is ed00, calls into the tape loader, which is in extended 0 page down there at the beginning of memory, to load the next chunks of game data. So the cheat code has basically started the Mixie load, or continued on the Mixie load. But the Mixie load is using the tape loader code at the beginning of 0 page. So we'll zoom through this load, and then we'll pick it up just as the game code is meant to start. But not quite, because it will go back into the cheat code. You'll notice actually that the Delta logo, as the tape loader is running, is actually flashing what probably is a sprite. And that's why the sprite registers at D000 and D001 weren't used for containing the code that was next to run. However, the Mixie load doesn't initialize all of the sprite registers, it leaves the other ones untouched, so that the memory, the code that was put in there, is kept safe. It's not touched, which is just as well, really. I mean, if the Mixie load was going to initialize all of the computer's memory, it would be very difficult to find some spare memory to put the cheat code software in there. But it would be possible to circumvent the memory clear, for example, and to stop that from happening, and to allocate a little bit of extra space for the cheat code to reside in memory still, but it doesn't need to do that, luckily. It can use the memory that's inside the VIC registers. So we're coming up to the end of the tape load, and there we go. The code at D002 has been called by the tape loader, which is all the way at the beginning of extended 0 page memory there. Actually, it's in the stack, because the stack is at 100 to 1FF, inclusive If we change the bank to be RAM, we can see that there's the RAM underneath the VIC chip. We want the bank to be in CPU mode, which is where currently the I/O chips, the VIC chip and everything else are mapped in. So this is what the CPU sees, is that the CPU finally sees this load and store, and then jump. This load and store is actually modifying the loaded game data. Now, the game is compressed, so I don't think that we're going to see anything really sensible. The fact that this looks like machine code with some weird instructions being used tells me that this is probably not going to survive when the data is finally decompressed. The data could be descrambled, it could be using an XOR, it could be using, what it does, it uses multiple passes of decompression. There is, I think, what looks like an RLE phase, something like an LZ based compression phase, some kind of dictionary being used. There is quite a lot of memory shuffling going on. So this final cheat code, where it stores 2 bytes into memory, is going to be modifying the compressed data, which will have all sorts of weird changes going on in memory, I expect. Or the 2 bytes that are being stored will have nothing, or probably have nothing to do with what it looks like in the final game memory once the game is actually running, because it's compressed data. So how these 2 bytes that are consecutively in memory at 3FA1 and 3FA2, how these 2 bytes translate to decompressed data is anyone's guess right now. Which is why this cheat code is actually really quite special. This cheat code circumvents all of the protection during the tape load, and it gets to this point where it modifies compressed data to get a beneficial change in the game code after it decompresses. And this jump to 2EB is the code which then sets up that message on the screen that we saw. The reading data, or whatever it is, please wait, whatever. The little white text across the middle of the screen, okay, which stays on the screen for quite some seconds actually, because it's doing all of that extra decompression. So this is why I say that the listings in the magazines for cheat codes were quite important from a way of learning how to circumvent the copy protection. Because if you can circumvent the protection, then theoretically you can expand on that work for doing the cheat code to not just do the pokes to give you infinite lives, but also to save out all of the data onto your disk and then load it in without having to do all of the extra loading stuff. You see? You could just save the memory at this point and then call 2EB, and then you'll have a game minus the protection, usually. We can try that by saving all of the data that we have in memory currently. If we have a look at the start of memory here as well, we can see that there is a message from whoever mastered the tape version. Wild save, copyright Interceptor Micros, 1988, written by Andrew Chalice, January 1987. Hello hacker, I hope you have fun with this loader. So again, we've got a nice little message for anyone looking at this part of memory. Let's just try using my compression tool just to compress, or try and compress all of that memory that we've just saved out. See if it does run. We'll call that entry point, which is at 2EB. Let's just see if it works, shall we? Ding, 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 ding. Now, of course, this is going to be restoring all of the data for the Mixi load as well, because the Mixi load was partially in memory at the end of the game load. And there we go. A single compressed file. Yes, it's got a lot of extra data in there from the Mixi load, but it kind of like proves the point, right? If the cheat code was extended to save out all of memory at this point, all of RAM, basically, which you can do, then you have a game minus protection. So this is why the cheat code listings in magazines was quite interesting, because it was a good learning opportunity. And the game does do a lot of decompression. You saw how long it stayed on that screen where it was showing that message. So that's what these kind of listings do. So here we are in my probably favorite tool, ICU debugger. We can see actually that the tape turbo load actually loads backwards through memory. We can see that in the memory view, but we can also see that in the way that the data is being populated. In the character set view, the text screen view, we can see the code at the end of the memory view there, writing from the end, so writing backwards through memory. A backwards turbo tape loader is quite an interesting thing to see. I mean, sometimes there are backwards decompression routines, yes, but a tape turbo loader that loads backwards is also relatively unusual, to be honest. The green line there progressing through is probably the loading text, I think, for the scrolling message. We can see here that the data, which is not, it doesn't look like sprites, right? It's just the way that the data looks, it's quite noisy. It doesn't have much structure to it, which tends to indicate that it's compressed highly or it's scrambled quite well. We can see the logo there doesn't have that flashing effect. It's definitely in the sprites there. We can see those 2 frames there for the sprite, for the flashing effect in the sprite. Again, we can see the backwards loading going on there in the text screens. There's a whole bunch of text there, so I think that's for the scrolling message. There's a whole bunch of greetings there, which is nice to see. We've got the text for the instrument names and the track names and the effects names and everything else for the music. Looks like it might be music data there. I think that's probably likely, right? So we hit the breakpoint. There we go. It's displaying the message. Please wait, reading in data. Look at the memory view there. It's doing an awful lot of scanning through memory, moving it around. There's the what looks like a dictionary LZ based compression, and then the final moving around, probably RLE based compression as well, moving around large chunks of memory. We can see all of the sprites there in the graphics map. There's a lot of sprites. We can see the sprite animation frames for the flames that leap out and try and hurt you in the background. So we now know that the background is obviously sprites. We can see the sprites get dynamically updated as the score data comes on, as the text comes on, shoot aliens and collect weaponry. We can see that message up at the top of the sprites bank. So the extra text which is appearing on the screen is actually sprites. We can see that the score information is actually coming up as sprites. When we start the game, it begins by copying in the extra rock formations, which I think is on the 2nd or 3rd or 4th attack wave or something like that, right? There's rocks of death first, and then there's ones after the rocks of death. There you go. The rocks get copied in to replace the jagged, kind of like a different kind of rocks. So these are the rocks of death, and they got copied in at the beginning of the sprite memory there. You can see they look a lot different. So there's dynamic sprite copying going on as well. And at the end of this attack wave, when the rocks of death disappear and fade out, so leaving the rocks of death. Whoops. Down, up, down, up. Oh, no need to go up. And then not very good at this game, am I? There we go. Blink. Right. Just looking for the Starfield screen. There we go. You see, there's the Starfield screen. And when we have a look at the Starfield screen, we can see that there's no text on there at all. Oh, yes, obviously the top and bottom borders have been opened as well. Sprites being displayed in the borders was a relatively common effect in games. It wasn't unusual back then. But I do love the way that the game uses a ton of sprites to display what looks just like text information. The Delta logo is all sprites. We'll have a look at the Delta logo, I think, in a little bit more detail. So here we are in C64 Debug GUI. We'll go into the Vic view. There you go. You can see the red borders showing where all of the sprites are. Basically, there's a ton of sprite multiplexing going on here. Yes, it's not a general purpose multiplexer, it's quite special cased, but you can see that actually there aren't that many characters in the character set. The character set is only like a couple of rows full. It's got what looks like big bullets, little bullets and stars, and then that's it. So the bullets from the enemies and the bullets from the ship are actually characters. You can see, look. The fish weapon, the three bullets horizontally, are actually not coming up with red borders, so it means that they're not sprites, they're characters, which is really quite cool. And we can see the bullet sprites are there actually in the character set. We can see all of the extra sprites. Wow, look at how many sprites there are on the screen. Isn't that fantastic? The advantage of doing it like this is that you don't have to stop the stars as they go behind characters, because they're not characters, they're sprites. So you get little twinkly star effects behind all of the graphics, which is quite cool, I suppose. But yeah, you can see, look, the fish weapon, the three-pronged bullet weapon, whatever it's called. I think it looks like a fish, right? It's comprised of characters. Yes, characters. So that's just fantastic, isn't it? And that's because, to be honest, the main part of the game area where the enemies are, uses 8 sprites, 7 sprites for the enemies plus 1 sprite for the player character. The attack waves seem like they have more sprites, but actually they really don't. It's just a very clever use of sprites. The areas where there's rocks of death and the areas where there are other formations at the top and bottom of the playfield are just very, very carefully designed and put together so that the enemies don't overlap that area where the sprites are. I just think it's a fantastically well designed game to get so much mileage out of using sprites like this. You see, look, 1, 2, 3, 4, 5, 6, 7 sprites for that formation plus 1 for the player character. That's all you need. The bullets and everything else are characters. And then you can see here there are 1, 2, 3, 4, 5, 6, 7 continuously recycling and scrolling on sprites. And of course there are 7 sprites for the rocks, and you need 1 more sprite for the player character ship, or the player ship rather. The player ship can go into those gaps between the rocks of death, but the enemy sprites never do. It's close, very close, but close is not completely overlapping. Even when those worms go wibbling up and down in the playfield, they don't really overlap the rocks of death. As you can see, that character in the middle of the screen, which I accidentally painted using this debug view, is still there through a gameplay session, through going back to the title screen. So actually it's not redrawing the stars in the background, it's just keeping on going. The stars don't erase characters which are there. There's no software scrolling going on, so we don't see it juddering around left and right in pixel steps. No, it's just there. Isn't that great? So the stars basically don't interfere with the bullets that are being shown for the enemies and for the player, the character-based bullets. They don't disturb the character-based bullets. So the stars kind of like appear behind the character-based bullets, only when those characters are not on the screen. Isn't that fantastic? So let's shoot over. Yes, you see it's the color. It's the character color. It's not the character cell itself. So yes, the player bullets don't seem to be interfering with the character color that's there. Okay, that's cool. You might notice that the screen color is actually being used to alter the star colors, because the stars are actually transparent, whereas the black is actually solid character data. Of course, this is extended text mode. That's why the character set data is so small. Extended text mode is where you only have 64 characters, but you have a larger choice of high resolution colors to use. So you've got the screen color and some extra background color, well, the extra foreground colors and background colors that you can use for the character cells. Okay. So that explains that then. So it's using high resolution extended color mode for the characters. Now that's really quite interesting. This allows you to have nice high resolution bullets, but using a greater range of colors that you could not normally use in this configuration on the screen. Anyway, if I paint some extra characters now, right, you can see now, you see that the screen color in the background is now showing through. So after the load has finished and we get this "please wait, reading in data" message, it calls some code which displays this message, but then it starts calling code which looks like decompression code. We've got a sys2064 there in memory, 2D and 2E, which are the basic end of program basic pointers, or rather the start of basic variable pointers, right? Those get set up with these values for this particular chunk of data, which is data which finishes before the mixi load data starts. So I don't think we need to save out such a large chunk of memory at the start of basic variable pointer. So I think we can save what looks like a basic program starting at 801, but not all the way up to FFFF. We can save it to the end of the basic program, or rather the start of basic variables. I noticed in the decompression code at 839 there, or the start of the decompression code, it's using 2D and 2E. So it's doing a memory move with the end of the basic program or the start of the basic variables. So we need to make sure that those are completely set up correctly if we want to load it from the kernel, for example. So let's try saving that. I think we might need 1 byte less, but we'll verify that by just oops, I saved out the wrong name, didn't I? I didn't put a PIG on the end. Let's put PIG on the end. So I'm just loading the file in to a separate instance of Vice now, just to see what 2D and 2E will contain in terms of what it thinks the end of the basic program is. It's important to get that right, because that's what the decompression code is assuming and relying on. So we'll put a break at 810, which is 2064 in decimal, right? This is hex. So, it's C1B6. So that's one too many, isn't it? Yes, it is. It's 1 byte too many. So we'll save out from the device monitor 1 byte less, B6, BF, there we go. And then we'll load that file in again to a separate instance of Vice. There we go. It's already running the decompression. There we go. Let's put a breakpoint there. Right, you see, that's correct, isn't it? C0B6. Right. Yep, that's the correct values. So the kernel load is restoring those correct values at 2D and 2E now. So we'll just let it run, and well, we're getting to a second decompression routine at 8:10. This time there's no sys statement. It might have been stripped out, but yeah, this is the second decompression pass. Is that a third one? Looks like the third one. And another. Oh, look, it's doing the EOR pass. We've got an EOR F1, F1E, EOR F1F. So yes, it's done. It's doing an EOR pass, so it's doing a descramble right at the end. Okay. So let's try compressing that already compressed and scrambled smaller file. And we can see it's not reducing it by very much at all, which tells me that the compression and or scrambling used within the original game data file is actually quite robust. It's quite good because it doesn't compress that much. So there isn't that much extra wasted space at all. So we don't need, I think, to compress it even further because we can't. So let's see if we can use the ICU debugger memory scanning tool to find the infinite lives cheat. So we've got 3 lives, so let's find all of the memory locations equal to 3 first. And then we lose a life, and then we find memory locations equal to 2. And it has narrowed it down almost immediately to be the memory location 12CB there. And we can see that when we set it equal to 1 after losing another life, so we have 1 life left, we've definitely, I think, found the memory address. So let's find the memory address of the instruction which updates that memory address. Let's find the, oh look, and if we move up a little bit, there we go, we have a decrement, a DEC instruction of 12CB, and I'm pretty sure that that's the only place in this code where the lives are decremented like that. So if we get rid of the instruction, or if we put, say for example, the value F in 12CB, and then continue, well, we're looking for where 12CB is referenced, and here 12CB is multiplied by 2, 4, and then 8 and 16. That's probably looking up the sprite data to update the lives count. And of course, if you have F lives, it doesn't display the number correctly. That's not a surprise. So we can see that the game still works if you put the value F, which is 15 in decimal, in there. It just doesn't display the lives properly. So I'm pretty sure now that 12CB is the count for the number of lives that you have. So let's get rid of the instruction completely. Here I'm using 3 no-op instructions. EA is the code for no-op, which is a single byte instruction, so we need 3 of them to obscure or to hide the decrement instruction with the absolute memory address. And there we go. So I can now continue on in warp mode, and the emulator runs this very quickly, and we can show that we are just looping around and around and around and around. We don't ever get to the game over sequence. So that's the memory address for the cheat code for the infinite lives. So tracing through the various decompression stages, we get to this jump to 1770 in hex there, and the jump is at 129 all the way down in the stack. So 1770 is the start of what looks like the game code. So I'm thinking if we have a look at the changes introduced by the cheat code that was in the zap listing, right? So we'll save this version of all of the memory at this particular address when we stop the execution of this address, which is a 1770 just before the game starts. So this version of the game does not have the cheat code applied. This is the compressed data. So what we'll do now is that we will apply those 2 bytes from the cheat code listing to the original compressed data. Those are 2 bytes, remember, that were being stored into memory by the cheat code right at the end of its load. We then let it run and hit the breakpoint again at 1770, and we save nearly all of the memory except the last 200 hex bytes. We'll call it delta cheat and 1770 now with cheat. Now let's do a binary compare between these 2 decompressed chunks of memory, and we have 1 byte difference, and there is that 1 byte difference. In this file it is at 3B D, right? 3BDC actually, but it's changing the CE with no cheat to a 2C with cheat. So it's changing the opcode by the looks of it. So the 2 bytes of the cheat code results in 1 byte only being changed in the decompressed game code. So change 2 bytes on the compressed input results in 1 byte being changed in the decompressed output. Unusual, but not unexpected, I suppose. Maybe the opcode which is compressed is expressed as a collection of bits split across 2 byte boundaries. And there you go, in the decompressed game memory there you can see the 2C is the bit absolute address opcode. So basically it changes the decrement instruction to a bit instruction. The bit instruction leaves the memory unchanged. So just adding a note to the debugging details there, it changed the decrement instruction, the dec instruction, to be a bit. So there we go, that's what the cheat code does, is that it just basically turns off the lives decrement. And of course, when you don't decrement the lives, you never run out of lives. So anyway, I think we can leave that video there. I just really wanted to go into some of the technical details of the game, and also, of course, show you how the cheat code listings published in magazines used to work. If you enjoy these kind of deep technical dives into my Commodore 64 Games retro memories, then please do consider liking or subscribing to this channel, and I hope to see you around next time. Have a great day, or have a great night or evening, wherever you are.